everybody, today we are going to start off the lesson by talking about a little bit of review of our inverse. So for number one on the bell ringer, what you're going to do is you are going to set up the work for the determinant. You don't have to distribute the 1 over the determinant outside. You just have to set up that value and then times your flipped around matrix. And then for part B, you're going to use your graphing calculator to determine the value of the matrix finding the determinant. Now, a reminder, when you're finding the determinant, like number 2, or even with the inverse, reminder matrix menu, second, and then if you edit your matrix first, you'll type in your size of your matrix. Reminder, the inverse of a matrix can only be found in a square matrix, so 2 by 2, 3 by 3, 4 by 4. And then once you select your matrix, if you go under the math menu, that will help you find the determinant. And if you want to double check your what the inverse of your matrix is, you would take your matrix and hit inverse to get that answer. Now for these two particular answers, what you should have had is for the first one, your setup would have looked like this. Remember 1 over the determinant, which is a times d minus b times c, and then flip-flop your a and d values from the original, and then negate your b and c to get that answer. In number 2, you had to use your calculator, because we didn't talk about how to do it by hand. You should have had negative 25 as your determinant for that 3 by 3. Now today we're going to shift gears a little bit. Activity 35 talks about how we can transform figures using matrices. And where we're going to start on this first example here is this triangle representing a portion of land, and they're representing it as vectors, or kind of think of it as points, but they're talking about them as vectors. Notice their wording here, so we're going to say A and B as opposed to X and Y, but same kind of idea. And the first piece of this, they want us to represent each of these points as a column matrix each. So what that means is we are taking our A and B values, or your X and Y values, if you want to think of them as like locations, points, and stacking them vertically. It's a column matrix. Officially, you can also organize your data as a row matrix, but we tend to not. For the book, they like to use column matrix, but you could use a row matrix officially. Now, if we wrote this as one matrix, notice here this is a 2 by 3 matrix in size. Again, if we had written it as a row matrix, it would have been a 3 by 2. Now, notice again with this graph here, they're telling us that this is 10,000 square feet of land is what this total grid is representing. So what that means to us is each unit, each linear unit, since the whole thing is worth 10,000 square feet, it's actually going to represent 100 feet. So if we actually should have plotted this land east and north of where it's at, what that means is we're going to have to take our figure and move it 2 units to the right to represent the eastward movement, and we're going to have to move 1 unit up to represent that movement up. Excuse me, that looks very bad. Up is what we're representing there. Now, our new matrix then, if we're moving everything to the right 2 and up, we're no longer at 2, 5. We're at 4, 6. We're no longer at 5, 10. We are at 7, 11. And we are no longer at 7, 3. We're at 9, 4. Okay? And mathematically, what we had to do to get these answers, if you flip the page in your book, so sorry, part C is on page 500, we took that original 2 by 3 matrix, and what we did is we added to the A components 2, we added to the B components 1 to get our new matrix C, which we wrote up above. So we're showing what operation we had to do, which is a very important piece of today's lesson. Okay? Now, take a moment to try that on your own. Represent the rectangle we have given as a matrix for part A. For part B, you're going to do as we did in part C, and you are going to show algebraically this set up and what your new matrix would be after that transformation. And then finally, we're going to talk about what negating matrix T that you wrote for part B means. Take a couple minutes, pause the video, do that on your own. Well, to check your answers for part A and B, our original matrix represented as column matrix using A, B, C, and D is this part here. And then we had to take matrix T and add it to our original matrix to show that transformation of to the left 2.5 units and down 3.5 units. Remember, A are our horizontal components, B or the second row is going to be our vertical components, and we get our final answer then of where this thing moved. Now, if we had taken matrix T and we negated it, what that means is that instead of everything being negative, these would all be positive, which means that instead of moving to the left 2.5, you'd be going to the right 2.5, and instead of going down 2.5, you'd be going up 2.5. Okay. Now, the next portion of these notes is going to talk about a different idea of planning using a city garden. Now, using those points that we had originally, we were at 4, 6, 7, 11, so it'll be somewhere up here, and 9, 4, so somewhere here. And here's our triangle, right? And we plotted this now as Bay and Main Street. And what they want us to do is look at these so that they are the same distance from Main Street down here though. So imagine we took this picture and we made it the same distance away from Main Street down below. What kind of transformation are we doing to move the original to the new piece, aka the pre-image to the image? Well, what we had to do here was a reflection, right? And instead of being at 4, 6, we're now at 4, -6. Instead of being at 7, 11, we're at 7, -11. And instead of being at 9, 4, we're at 9, -4. So specifically, we are a reflection over the x-axis, which means we were changing our y value. And at the top of page 501, extremely important here, notice this representation. Oops. Here, I'm going to highlight this representation. It's called a reflection matrix. And notice it's for the reflection over specifically the x-axis down here. Okay. And basically what is happening is we had to multiply our original matrix by this this reflection matrix in order to be able to get the result that we had here, because we weren't adding anything necessarily, we just were negating those y values. Now notice my placement as well of this matrix. It is extremely important that you place this matrix out front, because otherwise you will not get the correct answer, because your matrix multiplication wouldn't be possible. Okay, this is a 2 by 2, this is a 2 by 3. If we had placed this guy over here behind it, it would not be possible, because you would be trying to multiply a 2 by 3 by a 2 by 2 and the inner dimensions wouldn't match. So again, it's extremely important to recognize your order. Now again, the multiplication by the Rx matrix reflects it across the x-axis, and this is going to be true because we're keeping all of those x values the same, but our y values are being negated. And the problem here is we can't just multiply by a scalar of -1, because then everything would have gotten multiplied by a -1 if there was a scalar out front. So that's why it's really important that we had to do matrix multiplication versus scalar multiplication. So that's what part 8 is getting at. Every element would have had to have been multiplied if this was out front and not matrix multiplied by matrix. Okay. Now, for part 9, notice they are talking about the R sub y, the matrix reflection over the y-axis. So if we look back up at the original here for the reflection over the x-axis, notice this element was what was negated. When we talk about the R sub y matrix here, we need to be careful because we're going to represent this one with the first element negated now, the second one diagonal from it not negated, these are still 0. So again, this is going to reflect y-axis, aka all of your x values are what is going to get negated this time. So if we did that same multiplication that we did before, our y times c, that's going to actually now be our original matrix with these components, these x values or a values negated, while the second ones were all our b and y values stayed positive this time around. Okay. Now, if you multiply these values by themselves, so if you take r times r x and ry times ry, what you're going to get is it's going to result in our identity matrix, right? And we talked about the identity matrix a lot when it came to talking about inverse. And a reminder, that's just where it's positive ones along the diagonal, aka it's like multiplying by itself. If you reflect something over the x-axis and then you reflect it back again, it's just going to end up back in its starting location. Same thing with reflecting it over the y-axis. So what happens here is if you multiply, you take the reflection over x over the reflection over x, you're just back to the beginning. Okay. Now, the last little bit of the notes is going to talk to us about, oops, we're going to stay on this slide, but it's on the next page for you guys, page 502. And we're going to talk just very briefly about number 12, and that's going to be the reflection over the origin, which, if you think about that, is a reflection over the x-axis, and the y-axis is a reflection over the origin. Okay, so that would be, again, taking both reflection over x and then reflection over y. Now that actually is addressed a little bit in the check your understanding. I'm going to skip 13 for a second, but for 14, does it matter if we reflect over the x and then y to get the reflection over the origin, or could we reflect over the y and then the x to get the reflection over the origin? The answer is it does not matter, because whether I start here and go reflect over x, then reflect over y, or if I go this way where I reflect over y and then reflect over x, no matter what, I'm ending in that same location. So either way you write this is reflection over the origin. And then moving back to number 13, when you're reflecting over the x-axis and the y-axis, oh, that was 13, my bad. 14 then is asking us if we were to talk about reflecting a regular hexagon, how would this affect things? Well, if you reflect a negative or a regular hexagon, you're going to result in a 2x6 matrix because you have 2 points to represent each point, each vertex of your hexagon, and it's going to have 6 sides, so you would have 6 pieces to your matrix. Okay, so again, triangles would be like a 2x3, quadrilaterals 2x4, pentagon 2x5, and then hexagon is a 2x6. As far as your practice goes, you guys are going to do the quick check on this one. Oops, not the 32-2, the 35-1 quick check. And also from there, there isn't officially lesson practice I'm going to assign you from this unit or this lesson because it's not very good. You're going to do the activity 34 through 35-1 practice instead and check your answers to that, because that's going to kind of encompass everything from this unit and give you much more specific questions that are actually applicable. Okay. Thanks, everyone.